From now on, you have the essence of the points that we are trying to make about the mole concept. So what I have done here is to create a table here using those same three atoms we spoke about before: hydrogen 1, carbon 12, and magnesium 24 isotope. So using three isotopes there. Here is the atomic notation for the atoms. Here I'm giving you the nuclei so that you can compare their masses, and then putting there the atomic mass in AMU or U for each of these. These three columns are filled already. Then with your help, we'll fill this one here, right? And hopefully at the end of this, you'll have a more profound understanding of the mole concept. Now we'll do a little bit of seesaw activity. If you know to do seesaw, I'll give you a little quiz here. Look. Not quiz, but a little activity here. I'm going to ask you some questions here, and you help me to find the answer. Some you will not know. Here's a little balance here, like you do seesaw. In here, I put a mass of 1.0 gram. And I'm asking a question now. How many atoms of hydrogen are required to balance this mass? Of course, it's going to go down like this. Let us suppose that in an imaginary situation that hydrogen was represented by tiny specks of dust or something. And you were to count the dust particles. How many dust particles, if each dust particle represents an atom of hydrogen, how many hydrogen atoms will need here to balance this guy here? Anybody have any idea? I have 1 gram. How many atoms of hydrogen you think will weigh the same as 1 gram? The answer will be that it will be Avogadro's number, or 1 mole of hydrogen atoms that will weigh the same as 1 gram here. So this is 1 mole of hydrogen atoms. Therefore, what will you say about the molar mass for hydrogen? The molar mass for hydrogen will be 1 gram. Okay, so let's see what the point we're making here. 1 mole, or Avogadro's number of hydrogen atoms, weighs 1 gram. Since such a large number of hydrogen atoms weighs only 1 gram, then the mass of 1 hydrogen atom must be extremely small. So what to do now to find the mass of 1 hydrogen atom? We will take 1 gram and divide it by Avogadro's number. And this is what you're going to get. Or it is same as 1 U. Translated into grams, this is what it is. So now we'll fill the first row of the table there, where we will say that the molar mass of hydrogen now is 1 gram per mole. So see what happens here. This 1 U translate now into mass is equal to 1 gram, which is 1 mole. But for 1 atom, you have to divide that by Avogadro's number of atoms. So now in a different way to find this, if you take the mass of 1 atom, this is the mass of 1 atom, you have to cluster Avogadro's number of this before you can get 1 mole. So by multiplying by Avogadro's number now, these will cancel out here and you end up with 1.0 gram per mole. So look at some relationships. This is the mass number, it becomes atomic mass. This is the atomic mass. All you need to do is to change this U here into grams, and you get what is the molar mass of it. But of course, there's a shortcut, right? We established that by asking you first, in this case, how you get that, and then you told me that was it, right? Okay, so now we get the first row being filled. Let us now do another balancing act. In this case now, we use carbon. Same question again. If I have 1 atom of carbon here, how many atoms of hydrogen do we need to balance this? What do you think? Give you the answer. The answer will be this, 12. If you said 12, then you're right. So 12 atoms of hydrogen are needed to balance one atom of carbon. Now, we'll ask the same question again, but a different way. If I have 1 mole of carbon atoms now, a mole, how many moles of hydrogen atoms are required to balance this 1 mole of carbon atoms? All right, let's see what the answer is. 12 moles. If you said 1 mole, it will only weigh 1 gram. That is why we need 12 moles of hydrogen, which will weigh 12 grams, to weigh the same as 1 mole of carbon atoms. 1 mole of hydrogen weighs 1 gram, and we're using 12 moles. That must translate to 12 grams. And since this is balancing off 1 mole of carbon atoms, it means, therefore, that 1 mole of carbon must be equal to 12 grams. So the molar mass of carbon now is equal to 12 grams based on this little balancing act that we have done there to deduce that. So here again, we're using some logic, the same logics here. What you're seeing there is what you've already established there. But one thing more you have to talk about, okay? Okay. Now again, since this large number of atoms weigh 12 grams, thus, to find the mass of 1 carbon atom, we take 12.0 grams and divide it by Avogadro's number. So 1 atom of carbon will weigh 12 U, expressed in mass, in grams, will be this guy here. So now what do? We go now and fix up the second row of this table here. See? So look what happens. See some relationships? So this is equal to 12U, 1 atom, and is same as dividing 12 grams by Avogadro's number. 1 mole of atoms, so this is just a 1 atom. This column here is just 1 atom, atomic mass, right? This one here is molar mass, which is a huge number, Avogadro's number. So, okay, this is for 1 atom. So for me to know the molar mass, I have to cluster Avogadro's number of these here, or which is same as saying I multiply this by Avogadro's number, and you end up with 12 grams per mole. All right? Move on. Do another balancing activity. What do you think you get for this guy? Follow the same trend. What do you think you'll get here? If you say 24, let's hold that, then keep it there. Same question. How many atoms of hydrogen do you need to balance this 1 atom here? The answer will be 24 atoms. Okay? Now use 1 mole of this. And how many atoms of that now? The obvious answer is now going to be 24 moles. And again, since 1 mole of hydrogen weighs 1 gram, 24 moles of it must weigh 24 grams. And since this part here will be 24 grams, 24 grams of hydrogen are going to be here, then 1 mole of this must be equal to 24 grams. Right? And again, since all of these atoms weigh 24 grams, okay, 1 atom is going to weigh this, translated into grams, or same as this. So 24U is the same as 24.0 grams divided by Avogadro's number. And now we finish our table here by putting in this guy here. So again, look for relationships. This 24 here translates to 24U. All you do is to change that to 24 grams per mole. And this is for 1 atom. 1 atom is here. You multiply by the Avogadro's number, and you end up with the same answer here. But mind you, these values that they're getting here are only for this isotope here, only for that isotope there, only for this isotope here. Had you used tritium with hydrogen at 3, this would have been 3 grams per mole. Had you used carbon-14, then it would have been 14 grams per mole. I can't remember what's the other isotope. Had you used another isotope for magnesium, it will be in that and not this one here. So note that. So then, that is the concept of the mole. You want to talk about some other things now. This is hydrogen. It weighs 1 gram per mole, 1.0 gram per mole. And that will have Avogadro's number of atoms per mole. Same thing here. This will weigh 12 grams, 12.0 grams per mole, and it will also have the same number of atoms per mole. This, that, all of them. So 1 mole of any atom, even though they'll have different masses, they'll have the same number of atoms, which is Avogadro's number. The only difference with their mass is because each of these atoms here having different atomic mass. Okay, now, come back to this one now. Remember we said that to represent the atomic mass of carbon found in nature, we cannot use 14U, 13U, or 12U, but the average mass of these isotopes. Here we're showing you the 3 elements that we use: hydrogen, carbon, and magnesium. These are the 3 isotopes of hydrogen. These are 3 isotopes of carbon, magnesium, and here are their isotopic abundance. And of course, I show you how to do it for carbon. You can do it for magnesium, you can do it for hydrogen, where you find the average mass. And when you do that, these are the values that will ensue. And this is how now you will know how to find the molar mass for each of these. What you do, we use these. You'll see this in the periodic table. Magnesium will be 24.31. You'll have to use that now, change it to grams, and use that as a molar mass. What we're showing here is how the molar masses for naturally occurring elements that are having all their isotopes, are found. This is done by multiplying their average atomic masses by Avogadro's number. Of course, the same principle is used to find the molar masses for all the other elements, as the following examples will show. You're going to do here, if you multiply each of these by Avogadro's number, you'll end up with a molar mass for each one of these here. And this is the concept of the mole. This is how you find the molar mass for atoms, for all different types of atoms in the periodic table. So why don't we come back to this table a little bit more and talk a little bit more about this table here. So what this table is showing you here are 3 isotopes, one from each of 3 different elements. Hydrogen 1, carbon 12, magnesium 24. It shows you how each of these is heavy with respect to hydrogen. Carbon here with 12 times as heavy as hydrogen. Magnesium will be 24 times as heavy as hydrogen. So if you were to take 1 mole of each of these, magnesium will be 24 times as heavy as hydrogen. Okay, that's why you get 24 grams per mole. Carbon will be 12.0 grams per mole, because it's 12 times as heavy as that. 1 atom of an element is exceedingly small, okay, and it is expressed as U, so many U's, or if you take its molar mass and divide it by Avogadro's number, that gives you its mass in grams. So this is what it is for hydrogen. And if you cluster Avogadro's number of these, this big number here is a big thing here, that's Avogadro's number up here, it will amount to that for 1 mole. Do the same thing for carbon, you get 12 grams there, and for magnesium, you'll get 24 grams. I hope that was useful to you. Okay, try my best for people to see a big picture and to try to remove as many misconceptions as possible, so you can go back, you can see the video again if you didn't understand anything, and I hope that that explanation was useful for you. See you next time again.